So hi there, I'm just going to continue with the series of videos on matrices, and I'm going to be considering a matrix M, a transformation matrix, and working out its eigenvalues and eigenvectors. This is actually quite a challenging part of the course conceptually, but my best explanation really for what an eigenvalue and an eigenvector is to do with how points are transformed by a matrix, in this case M. So just by way of example, if I put a vector, an arrow, and I move from my point, for example, C to C dashed, you'll notice that if I extend that arrow, it does not pass through the origin. Okay. What we have at the origin is an invariant point, and if we can establish a line where, for example, it passes through the origin where a point moves along that line under the transformation, in this case M, and passes through the origin, i.e. D moves to D dashed along that line, then that will be, the arrow actually represents an eigenvector. That eigenvector would shrink down to its most straightforward form. So in this case it would be -1, 1. So as you say, we stretch that out and you'll see that D maps onto D dashed along that line. And how far along that line it moves depends on what's called the eigenvalue. It's like a scale factor. Okay, so how do we work these things out? Well, what I'm going to do is I'm going to basically say that an eigenvector I'm going to define as U, and it's a set of xy coordinates whereby if I transform it by matrix M, it becomes some scale factor lambda of xy, i.e. it scales along that the vector xy. So if that is the case, then xy in this case is the eigenvector and lambda is the eigenvalue. Okay, so based upon that, what we're saying algebraically is mu, matrix M transforms xy up to our points, which I'm going to define as the eigenvector, basically creates a scaled up version of itself. Okay, so mu equals lambda u. You may have seen this before. I can manipulate this and basically say that mu minus lambda u is equal to 0. I'm going to then take out, as I can, because it's associative multiplication, a factor of u, the eigen vector that we're looking for. And then I'm just going to sneak in, and it might seem strange that I'm doing this, the identity matrix I. Okay, so I'm multiplying lambda by I. That's actually okay because the purpose of that is to create a matrix out of a value, a scalar value. So basically lambda times I simply becomes lambda 0, 0 lambda. Okay. Now what we're looking for is a zero solution for this, for non-zero values of u. So we don't want u to be 0, okay, because otherwise it's completely ineffective and we don't actually find the eigen vector that we want. So we're looking for the solution for m minus lambda I equals 0. That means that there is a unique solution to that situation, and if there's a unique solution to that, that basically means the solution is singular, or sorry, it's a singular matrix, i.e. the determinant of that matrix is equal to 0. So this is our condition to establish our eigenvalues and eigenvectors. Okay, so this is our starting point. So on the top right is our condition or the very definition of a eigenvector. So our transformation matrix M multiplied by U will give us some scalar multiple of U. Okay, so what does that actually mean? So again, we're going to do mu minus lambda u equals 0. Okay, so it's effectively rewriting the same thing. And then we're going to basically say that mu minus lambda iu equals 0 as before. Now I'm going to take out a factor of u, so m minus lambda I multiplied by u equals 0. Okay, so we're looking to create a matrix which is n minus lambda I in each case. Okay, so for example, we're going to start off with lambda equals 2. Okay, so for that condition, we end up with the n minus lambda I matrix is going to end up becoming equal to 4 minus 2 times 2, and 2, and then 1, and then 3 minus 2. So we end up with a matrix that looks like this. And what we're basically saying is if we multiply it by u, and u is undetermined currently, but we established it was going to be some set of coordinates x, y, and we know that that's going to be equal to 0. So we go ahead and multiply that matrix out. We're going to end up with 2x plus 2y equals 0, which distills down to x plus y equals 0. Okay, so that's our first multiplication done, that's our top line, and then there's our first equation, and then our second line is just going to be x plus y is equal to 0. So those two are actually consistent, they agree with each other, so we have found our eigenvector. If you want to rewrite that as a conventional y equals mx plus c, there will be no value of c because all eigenvectors pass through the origin. We can just simply rewrite both of those because they're going to be the same thing, y equals negative x. So that is our first line of invariance, where a point will scale along that line by the eigenvector, the eigenvalue 2 in this case. Okay, so we're going to go ahead and do the second one, exactly the same process. So let's give myself a little bit of space. Okay, and now we're going to run parallel to that, and we're going to set lambda equals 5. Okay, so the same n minus lambda calculation. It's going to be 4 subtract 5 is negative 1, 2, 1, and then 3 subtract 5 is negative 2. Okay, and we're going to multiply this by another point x, y to find our second eigenvector. Okay, that's a rather large looking 0. And if we multiply this out, I get negative x, this is our first one again, plus 2y equals 0. And our second one is going to be x minus 2y equals 0. So actually they are multiples of one another. We can basically multiply the bottom one by negative 1 and it becomes equal to the top one. So once again they are consistent. So we're going to rewrite those and we're going to end up with 2y equals x. So I'm just using either of those is going to give it the same result. Okay, so in our y equals mx plus c or y equals mx form, we end up with y equals a half x. So that is our second eigenvector. So we have an eigenvalue associated with the first one as 2 and an eigenvalue associated with the second one as 5. So those are our two bits of information. Anything along the y equals negative x line scales up or multiplies out by a factor of 2, and anything along the y equals a half x scales up by a multiple of 5. So we're going to see that in action now. Okay, so here's our unit square A, B, C, D, and our transformation matrix M, which is on the top left, 4, 2, 1, 3. So if I show the image, at the moment it's just a point, so I'm going to scale it up as you'd see it expand, and notice D dash, which is our image of D, it passes straight through and continues to expand until I fully have the scale factor of 1. So, so D maps onto D dashed. Along the line, if you remember, the eigenvector y equals negative x. So if I can now pick up my point D and move it up and down that line, you'll see that it scales along that line. And if you look at the unit scale factor, it's gone from 0 to D is 1 diagonal unit, and 0 to D dash is 2 diagonal units corresponding to an eigenvalue of 2, scales up, doubles, doubles, and continues to double up and down that line. Anywhere off the line, it's actually no longer an eigenvector. Okay, so I'll pop that back where it was. If you also remember, the other eigenvector was y equals 0.5 x or a half x. So I'm now going to take my point C, move it around. There's no actual linear scaling because it doesn't pass through the origin until I drop C onto the eigenvector y equals a half x, and it scales up and down that line. I can also go up to this eigenvector or back down the y equals half x in the other direction. So you'll see it scales in all directions along those eigenvectors. So if I just choose a point here, 2, 1, this corresponds to an eigenvalue of 5. That's the eigenvector y equals half x. So C to C dash is 5 times as far from the origin. So 2 scales up to 10 units, and then 1 up corresponds to a scale of 5 units up. Okay, so it's scaled up by a factor of 5, as we expect. Okay, so I hope that's convinced you the nature of eigenvalues and their corresponding eigenvectors. So thanks for watching.